Well, thank you. Welcome to Winter Flying Refresher. My name is Scott Dennstaedt. I'm a CFI and former National Weather Service research meteorologist and founder of aviationweatherworkshops.com. It's co-authored with a meteorologist, Captain Doug Morris, who is a Boeing 787 captain for Air Canada. All right, so here's the topics we're going to try to cover tonight. I'm going to do a brief introduction and finally get into the various airframe icing factors, including temperature and drop size. Also, I'm going to talk a little bit about the icing analyses and forecasts, as well as what you can draw from surface observations, and also looking at the 3,000-foot rule. Well, first of all, icing is a very complex subject that requires a challenging dialogue. It's just something that is very complex, and certainly we'll be talking about a lot of various different terms in this particular webinar. You also have to understand the science and meteorology behind this. Ultimately, it's not just about understanding the basics. We really have to dig into some of the aspects of icing to really get an appreciation for what causes icing and how we can avoid it. And we also have to understand the weather guidance and its limitations. Limitations are really important here simply because you want to make sure that you're using the product the way it was initially or intended to be used. And also you really want to understand and learn how to integrate all this guidance, and there's really no perfect way to do this. I'm going to touch on that a little bit, but ultimately there's no perfect way to integrate all this guidance. So the focus really should be on being situationally prepared. Not about being right or wrong per se, but being situationally prepared for what might occur. So I know that a lot of people approach me and say, Scott, you're a CFI and you're a meteorologist. You must have this great approach to your pre-flight analysis. And the answer is I really don't. Per se. I use what's called the funnel approach, and that is I start with the big picture, those big picture elements which really drive most of what I grab from the weather, and then I work my way to the details. And once I get to the details, I'm really filling in the gaps of what's missing from that big picture. But most of my decisions when I fly myself associated with icing or thunderstorms or any weather event, it's what occurs with the big picture that's really important here. Now, should I fly IFR or VFR from the perspective of icing? Well, obviously the risks of airframe icing are generally higher when you're flying under instrument flight rules, and that's just because you're exposed to more hazards in the sense that you can fly in the clouds and precipitation when the temperatures are appropriate for icing. So that puts you at a greater risk flying under IFR. However, even under VFR, you can get freezing rain and drizzle. In fact, in most cases, when we look at some of the icing accidents or incidents, 1/3 of those cases falling to the surface was freezing rain or freezing drizzle. So we do see a fair amount of accidents associated with that, not only in the clouds, but essentially below the clouds themselves. And certainly data link weather, like from SiriusXM, can help to identify instance of precipitation and potentially its type as well, whether it's falling in the form of rain, snow, or potentially even freezing precipitation. Well, let's talk a little bit about the airframe icing factors. So what are the basic ingredients for an encounter with icing? Well, I think it's a teaspoon of poor planning, a dash of an unprepared pilot, and a pinch of an imperfect forecast. And I know you were thinking that it was flying in visible moisture with an aircraft surface temperature below freezing. But I look at these three and pinpoint when we look at accidents or incidents related to icing, it's usually one of those three that we find is at fault. And the last one, I want to make just a quick comment. We know every time a forecast is issued, it's incorrect from the very beginning. We know that. It's imperfect, but you can learn to draw truth out of these imperfect forecasts, and that's really the goal with respect to icing, drawing all that truth and being situationally prepared. So supercooled liquid water is the nemesis of pilots in the wintertime. Essentially, that's water in the liquid state when the static air temperature is colder than 0 degrees Celsius. When the outside air temperature is colder than 0 degrees Celsius and you have liquid in the atmosphere, we call that supercooled liquid water. Now, the term freezing level is really somewhat of a misnomer. If I were king, I would be changing that to, say, melting level. But unfortunately, freezing level is one of those things that have just come along with the baggage, and we've been using the term freezing level for a long period of time. But certainly we know that liquid water doesn't have to freeze because it goes below 0 degrees Celsius, but it does have to melt. So a frozen precip has to melt when it's warmer. So most freezing of liquid water is what's called a heterogeneous event. That means it requires a nucleation event to occur before you can get freezing. So when we talk about supercooled liquid water, you can't think of it the same as bulk water, like a puddle outside your steps. Let's say we had a little bit of rain that fell the previous night and it developed a puddle, and the temperature just dropped a little bit below freezing. You'll start to see that puddle freeze over. We call that bulk water situation. And it's not really the same as what happens in the clouds, because there's enough dirt in that puddle to allow for freezing to occur. But when you look at icing, on the other hand, you have to think of every single cloud drop as a separate puddle. So each must go through its own nucleation event. And it turns out that those nuclei out there perform two different functions. One, for condensation, so we can get drops, liquid drops in of itself, but there's also something called ice nuclei, and they're relatively rare compared to those condensation nuclei that we get for drops. So there are three basic factors associated with airframe icing, and that includes temperature, drop size, and liquid water content. Now, we're not going to talk about liquid water content in this session, but I'm going to focus on the two that most pilots learn about, and that is temperature and drop size, so we can review those. Now first, let's talk about temperature. It's real important to understand what the freezing level is all about and where it is. Like the American Express commercial years ago, don't leave home without it. So you don't want to ever depart, even during the summertime, unless you know what's happening with the freezing level. My worst icing incident that occurred was actually in July at 13,000 feet. So you really want to understand what the freezing level is, because you might get into a situation where you might be in temperatures below freezing and in that visible moisture. So understanding where that freezing level is will essentially allow you to make better decisions. And so I think the lowest freezing level is one of the keys to knowing what your exposure is to airframe ice. And so icing becomes more likely if you're flying in visible moisture and that outside air temperature is below freezing. So how do you determine the freezing level? There are a number of different ways, but one of the ways that you do not want to use, and I overemphasize this, you never want to use the standard lapse rate to estimate the freezing level. I see too many pilots out there that use the surface temperature, and they say, well, they taught me that the standard lapse rate is 2 degrees Celsius per 1,000 feet, so I'll calculate that freezing level based on that. Well, the problem with that is the atmosphere is rarely standard, and in many cases it's actually greater than standard. So if you do that little trick of using the standard lapse rate, what's going to happen is you're going to calculate a freezing level that's actually higher than it really is. So we need to understand that we don't want to make estimates on the freezing level. Instead, we want to use a good source. And certainly when you're in the air, SiriusXM provides a great source of the freezing level while you're en route. So I like to tell folks, use a deterministic forecast, not any kind of any particular kind of rule of thumb here. In this case, you're going to use something like the GAirMets, graphical airmets, and you can get those from aviationweather.gov. They'll actually show you the freezing level over the next 12 hours. Or you can use the lowest freezing level forecast as well from aviationweather.gov. Gives you a really good kind of indication of where that freezing level is, and you can plot your route along that as well and get a sense for whether you're going to be dealing with temperatures at or below freezing at your altitude. And if you're a real geek, you can actually then pull up these things called skew-T log P diagrams. And in that particular case, you'll see here that you've got that area right here where the freezing level is in the sense of being able to determine how high you have to be in order to reach that particular freezing level. So it's a really good indication of over a particular point where that freezing level may be, and you can look at this out to even as much as 24 hours in the future. And the website for that is rucksoundings.noaa.gov. Now, airframe icing is really limited to a layer of the atmosphere between 0 degrees Celsius and minus 40 Celsius, and so that basically is a pretty big range, but it's extremely rare below about minus 30. In fact, Environment Canada in an instrumented airplane found supercooled liquid water down to a temperature of minus 37.5 degrees Celsius, and that was actually in a thunderstorm. So essentially, when you look at the big picture here, airframe ice is really restricted to flight level 300, 30,000 feet or below, outside of any convective activity. So that's a lot of places, essentially, where most of us fly happens to be below those altitudes. So it's actually rare to see any kind of graphical air met for non-convective moderate airframe ice issued above that. Now it can happen, it's not essentially limited, but we rarely see that. Most of the time it's again limited to below flight level 300. So if you fly a piston aircraft, this essentially leaves us very vulnerable to airframe icing. Now, sub-freezing static air temperatures that are in that 0 to minus 25 are the most concerning. In fact, you can even narrow that down even further when you start getting into temperature ranges of 0 to about minus 15 Celsius. That's when you're dealing with the highest risk of airframe icing when you add visible moisture or even precipitation other than snow to the picture. And so when you look at a graph here, and this graph is represented essentially by a study that was done for taking a bunch of pilot reports. So we had pilots reporting where they were picking up ice, and then they mapped out the temperature using a numerical weather prediction model called the rapid update cycle, and essentially they plotted that, and the numbers of reports essentially were plotted on this diagram. What you see here is, again, looking at the maximum area in that curve. Again, that's at temperature from about 0 to about minus 15, where we see the most the highest number of reports for icing. So if you're in that range, you're likely to find yourself in icing conditions with respect to being also in visible moisture. Now, looking at this, you still see there's a number of reports that are essentially fairly cold that still have icing. So don't use that minus 15 as a hard line in the sand. It's just that we trend away from that. Essentially, we're trending down towards no pilot reports as we approach that minus 40 limit. Now, as the air temperature gets colder, essentially once you get around minus 12 or so, we start to activate those ice nuclei, and then we get to a point where we start to trend towards less and less supercooled liquid water in the clouds. And then when we get to about minus 22, we start to see that ice crystals become more dominant than supercooled liquid water. So essentially what happens here, as you start to develop ice crystals at minus 15 and minus 18 degrees Celsius and colder, they essentially, the atmosphere starts to build bigger ice crystals and starts to evaporate some of those supercooled liquid water drops, and then we end up with, in some cases, with a mixed phase cloud. So not only do the ice crystals float around and start to pick up or rime a lot of those liquid water drops that are out there at colder temperatures, but it also, we see the evaporation of those liquid water to build bigger ice crystals. So one of the things that you want to look at here is, and it's a key element that a lot of forecasters look at, and that is the cloud top temperature. So when the temperature of the cloud top is warmer than about minus 12 Celsius, that means the cloud below is likely dominated by supercooled liquid water. So A cloud top temperature of -12 and cold and warmer, you're going to be guaranteed to have liquid in that cloud below. So the way to look at this, one of the ways to look at this, again on aviationweather.gov and some other apps will show you a color enhanced infrared satellite images. And you'll notice on the bottom here there's a scale, and this is in degrees Celsius, and this is basically just showing you what the satellite is seeing in terms of temperature. In some cases it may be seeing the temperature of the ground, like here in Alabama, Georgia, and Florida, but it also may be seeing the temperature of the cloud tops. And anywhere you see the orange, yellow, and kind of pale green colors, you know you've got cloud top temperatures that are in the range that where we see the most icing occurring. So you know that that cloud below this area here in Georgia is going to be dominated by liquid water. All right, so again, the role of temperature in terms of the cloud top temperature, you want to look at this particular image and look for those temperatures that are showing this green and yellow and orange colors, because we know that the clouds here in Georgia, the cloud below that is going to be dominated by supercooled liquid water. Now, if you go into the areas where there's much colder temperatures, like here in Northern Virginia, where you're starting to see the kind of the darker blue colors. In those particular instances, you're going to probably be mixing in a lot more ice crystals in those clouds. Again, not saying that you'll be guaranteed not to have any kind of liquid water in those colder cloud tops, but they tend to seed the clouds below, and we tend to see a more mixed phase, or even sometimes glaciated clouds below that level. All right, let's now talk about drop size. Any aircraft with a certified ice protection system are permitted to fly into what's called small drop icing environments. Small drop icing environments. It turns out that no aircraft has ever been certified into a large drop icing environment. But if you look at most large turbofan aircraft, all your commercial airliners out there, they've never actually been certified into these large drop environments. Instead, they operate under a waiver for that. So what is a large drop? Well, you might find it's really not all that large at all. So we call that large drop scenario super cold large drop icing, or SLD icing, as you might have heard. So essentially this is an environment where what's called the median volumetric diameter is greater than 50 microns. So if you're micron challenged, like most pilots would be, 1 millimeter equals 1,000 microns. So essentially, imagine taking a cubic meter of air and finding all the drops in that and lining them all up in a straight line by their size. And when you find the median size, that's essentially the MVD, or the median volumetric diameter of that particular environment. And when that is larger than 50 microns, there's going to be some smaller drops, but there's going to definitely be larger drops. We call that an SLD environment. Now, there's no way for us to know that we're flying into it specifically, but we can look at forecasts and we can look at certain signatures that will alert us to the fact that we may be in a large drop environment. So just to get a good perspective here, the average diameter of a human hair is about 100 microns. So when these drops, this MVD gets about half the size of a human hair, barely visible to the naked eye, that's a large drop environment. So large is not really all that large at all, and no aircraft has been certified into one of those large drop situations. Now, so here's the three different situations that you're going to see larger drop scenarios. One is in what's called moist convection, especially deep moist convection, cumuliform clouds, those clouds essentially that have those hard edges and kind of look like a cauliflower kind of appearance, and these can turn into obviously thunderstorms, cumulonimbus clouds. So those clouds themselves usually have larger drop sizes in them, especially near the tops. Now, freezing rain and ice pellets, and we'll talk about ice pellets a little bit later. Freezing rain is a guarantee. We're talking about 3,000 microns for an average size raindrop. That is definitely SLD. And even freezing drizzle, somewhere around 200 to 500 microns, is what we usually see there. So freezing rain and freezing drizzle are your typically the ones that most pilots understand and know about. But if you ever fly in the summertime at temperatures below freezing and you start getting yourself into some of these cumuliform clouds, you're going to notice that you're going to pick up a fair amount of ice in those clouds, and they're going to be typically large drops. Now, what were you taught when you encounter freezing rain? So most pilots are taught to climb, but why is that? Well, they're told that there has to be some warmer air above your flight level in order to get freezing rain. The idea is that snow is falling into a warm layer that melts it above freezing, and that falls into a sub-freezing layer as freezing rain. So hey, there's a warm layer up there somewhere, so if I climb I can probably get into that, but we're going to find out that that's not the normal case here. So freezing rain is mostly a ground hugging event. It's not something you're going to be flying around at 10,000 feet and fly into. That can happen, it definitely does happen, but it's not the norm. It's a ground hugging event. So you're going to typically encounter freezing rain while you're flying, let's say VFR or even IFR below the clouds, or on approach to land or on departure. So essentially, anytime you're going to encounter freezing rain, it's going to be near the surface. So it's not like you're flying along at 10,000 feet, you hit freezing rain, you go, oh, remember that, what they told me to climb. That's really not the case. Most of these situations are really close to the ground. So let me show you kind of the different conditions that generally occur and kind of look at their occurrence themselves in terms of percentages. So most pilots are taught about this particular element. This is called classical freezing rain, or the classical SLD. This is what we say is the classical structure that you're taught. And that is, we have snow producing clouds. These cloud top temperatures are really well below freezing. Remember earlier we talked about that on the infrared satellite image. When we start getting cloud top temperatures much, much, much colder, we're generally going to be dealing with snow in the clouds and snow producing clouds. And that snow falls through a warm layer, call that a warm nose. It's temperatures above freezing, and that melts the snow into rain. And then that falls into a sub-freezing layer, and then we get freezing rain. And again, this is usually near the surface. Well, that turns out that this structure that I'm showing here only accounts for 8% of the freezing rain events. It turns out that the next two that I'm going to show are more common, and that is, we call these non-classical freezing rain. It's a non-classical structure. And so essentially we have the same situation, except we have warm cloud top temperatures. These are not snow producing clouds. Instead, they actually just have liquid. So this is all liquid in these clouds. There may be a few ice crystals mixed in here and there, but because the temperatures are warm enough, they tend to be dominated by liquid. And that could fall in, and typically it falls out of the cloud as drizzle rather than rain at temperatures above freezing. So there's that warm layer again, and then that falls into a sub-freezing layer. Again, usually is freezing drizzle, but could be freezing rain. But most of the time this is typically kind of closer to the surface. Or the other possibility, and this is the one that kind of surprises most pilots, is in this particular case, same kind of classical, non-classical structure here. What we have here is the same kind of thing, very warm cloud tops, warmer than -12 Celsius, and again dominated by liquid water below freezing, and that falls into a sub-freezing layer. Well, basically there is no warm layer here. The entire temperature profile is below freezing. And this happens actually quite a bit. In fact, the last two that I showed, these non-classical, account for 92% of the freezing rain events, which are an all liquid process. There's no snow at all in this entire process. And that tends to go against what most pilots are taught. So essentially you're taught the exception and not the rule. So this is the rule that we're generally see in terms of freezing rain and freezing drizzle events. Now here's a good also a kind of depiction in terms of the depth here. So red is that classical structure that you're taught, And the black is that non-classical that we just covered. And this is the percentage of cases that we see in their layer depth. So the layer depth would be, let's say, for instance, 500 feet above the ground, that we would have a freezing rain kind of event. You can see that 23% of the cases happen at 500 feet or below near the surface. And you go up to 1,000 feet, there's another 18%, and then at 1,500 feet, you can see there's another 15%. So at 1,500 feet or less, we see over 50% of the freezing rain events that occur. So this is definitely a ground-hugging event. This classical structure is definitely ground-hugging. Now, the non-classical structure we see is spread over a lot larger area. In fact, you can get some depth to these much greater than 10,000 feet in some cases. So that's why this non-classical case is more significant. In fact, there was an accident back in 1994 over Roselawn, Indiana, where an ATR-72 ran into this non-classical structure and unfortunately lost control of the airplane and killed everybody on board. So that non-classical structure happens quite a bit. Now, if you are looking for the big picture, some of the things you're going to look at, and there's many different scenarios that can come up here, but the one that happens a lot here on the East Coast is we have a fairly large area, cold high pressure up here in New England or up into New Brunswick or even up in Nova Scotia, and that brings in kind of moisture and cold dense air near the surface, and that wedges up against the Appalachian Mountains. We call that a kind of a wedge event, and we call this cold air damming. So all that cold air is dammed up against the mountains, and this kind of warm air from this low and the south kind of rides up and over that cold dense air, and that's what produces typically that classical structure that we looked at, where snow falls into a warm layer and then falls into that sub-freezing layer for that cold air at the surface. So you can start to look for this during the winter time, this kind of a structure. That's where we'll typically see these classical freezing rain events. In fact, the area from Charlottesville, Virginia down to Charlotte, North Carolina is that kind of the classical capital of the United States for that classical structure. All right, so let's talk a little bit about the icing analyses and forecasts that you may be able to use. Well, pilot weather reports are one of the best because obviously pilots that are witnessing icing situations or even in clear situations where they're not getting ice are really important to understand. We're not going to talk specifically about that. Instead, we're going to look at the color-enhanced infrared satellite imagery, the current and forecast icing products, which include a probability, severity, and SLD forecast, as well as G-airmets and SIGMETs for non-convective airframe ice. And all those that you see here are found on aviationweather.gov. And you also can get some of these as well on your SiriusXM broadcast. So let's take a look at a situation, and specifically I'm going to look at this area right here at the border between Indiana and Ohio, and we definitely see some clouds here. Now there's some really bright clouds down here, which are some areas of convection, some thunderstorms that are occurring, but let's just take a look at this kind of not as bright white cloud in this area here in kind of the central part of Indiana and Ohio. And let's superimpose over that this infrared color-enhanced infrared satellite image. What you'll notice is in this particular area we have the convection. We have really deep clouds. These are really cold cloud top temperatures signifying very tall cloud tops, definitely convective in nature. But look at the colors here that we're showing in the in this particular region. They're basically looking at some kind of light green to maybe even mostly yellow areas, and if you remember, that's the color that we see that we have a lot of possibility of structural icing, of airframe icing, because the temperatures, the cloud top temperatures are fairly warm here. So we know in this particular case the clouds are dominated by supercooled liquid water. So this is one of the first things I go to when I look at my route. I want to find out which clouds are definitely going to be an icing threat, and I want to make sure I plot to avoid those. The other product is an automated analysis tool called the Current Icing product, and it came out back in the early 2000 range, but I think it's also a good way to kind of get an understanding of the big picture with respect to icing. And let's look at that same area again where we saw that there was some really warm cloud top temperatures. And sure enough, we see the colors here represent the probability that icing occurred at the top of the most recent hour. In this case, it's like 17Z. And we see that the numbers here, the probabilities, are up there in the 60s and 70s and even higher percentages. So we do have an indication here that we've got some serious icing hazard in this area, and that again is bolstered by the fact of what we saw on that infrared satellite image. And if we look at the severity product, which basically tries to categorize this in a categorical way with trace, light, moderate, and heavy icing, you can also see that we're dealing with the possibility of some moderate ice here. That's the color is here is a moderate. So not only do we have a probability of icing, but we also have a good chance that this will be a moderate area of icing, something certainly even with a certified ice protection system we want to be very careful about. And if you look at the last product, which is an overlay, which is the SLD, super cold large drop icing, and that's that kind of red hatched area that you see here, you notice that all in that convection further south, there's definitely a lot of region here where we see SLD. We expect that due to the convective threat that's occurring, but we even see up here a little bit further to the north where we were looking, there's definitely a few spots here where we see SLD threats presented. Now, it's important to understand that this particular chart, even if there's a minimal chance, a 5% or greater chance that SLD could be in that area, any signatures at all, even the most remote chance, they're going to show SLD on this chart. So it really doesn't give you, it's not a calibrated probability, so it really doesn't give you the full threat of it. But nevertheless, it is showing here that there's a possibility of SLD. Now, graphical air mets are the official product that the official advisory that you're supposed to be looking at now. They replaced the Legacy AirMet back in 2010. They have a higher temporal resolution than the Legacy AirMet, although the Legacy AirMet is still around, but it really shows you kind of at a broad level where there's a possibility of icing, and it includes the top of the icing layer, in this case 25,000 feet, as well as the base of the icing layer. In this case, it would be 12,000 over here on the left and 24,000. And if the bottom has two numbers here, that means that in this particular case, that means that the freezing level varies over this entire area from essentially from 12 to 8,000 feet. So if you're in that region and you're in that range from anywhere from as low as 8,000 up to 25,000 feet, you have the possibility of running into moderate airframe ice in this particular case. SIGMETs are probably the worst icing that you're going to experience are going to be covered under SIGMETs. Now, the important thing to understand about SIGMETs is that they're generally only issued once pilots start reporting those conditions. So SIGMETs are not necessarily somewhere a forecaster is sitting down thinking that there's going to be severe ice in this particular region, but instead they're waiting for pilots to start reporting that ice, and essentially they'll map off an area, we call that the SIGMET area right here, and that will tell you that there have likely been areas of severe ice reported in that particular region. In this particular case, there was a couple of UPS freighters, one coming from Seattle and the other coming from England, that reported some severe ice at 3,000 and 4,000 feet, and that caught the attention of the forecasters at the Aviation Weather Center, and they issued a SIGMET for severe ice. So SIGMETs essentially live and die by pilot weather reports. Now let's take a look at surface observations and what they might be able to tell you. So first of all, anytime you see a METAR that has any kind of freezing rain or freezing drizzle, or rain or drizzle, it's basically telling you about what's reaching the surface, and that includes also terminal forecast. So it's really telling you that this is expected to reach the surface. Now, ultimately, if the temperature is just a degree above freezing, you're not going to get freezing rain or freezing drizzle at the surface. And forecast TAFs will not be forecasting freezing rain or drizzle. Essentially, you might go up just even 500 feet or so, and you might find yourself in a really nasty SLD environment. So be careful of that. Just because you see METARs and TAFs that are not showing freezing rain or freezing drizzle doesn't mean that that doesn't exist aloft, especially when we start to see temperatures hovering just above freezing. Now, it turns out that freezing drizzle, an ASOS cannot automatically report freezing drizzle. AWOS can, but essentially anytime you see an ASOS report freezing drizzle, it's augmented by a human observer. Essentially, we haven't really found equipment that will report that. You might say, well, I've seen it before. Typically, they'll report unknown precipitation, but the AWOS itself can report it, but actually it's inferred. So, anytime you infer something, essentially it's drizzling and the temperature is below freezing, so therefore it's freezing drizzle is how they infer it. When in fact the ASOS for freezing rain actually allows the liquid to freeze onto a probe, and then they melt that off and it refreezes again, so they can sense that it's freezing on that probe, and so therefore they can be really comfortable. Freezing drizzle, they have not really found a good indicator for that for an ASOS. So again, if you see unknown precipitation type from an ASOS, that may be because you're dealing with a freezing drizzle case in that regard. So anytime you see PL in a METAR, that's essentially ice pellets, and it's colloquially known as sleet. It's actually a good indicator for SLD aloft, for that large drop scenario we talked about. So anytime you see ice pellets themselves will bounce off the airplane and probably take some paint off with it, but it's not an icing threat of itself, but it does tell you for sure that you have SLD conditions aloft. And here's why. Essentially, remember that first classical structure. So essentially, if you have ice pellets hitting the ground, what you know is that you started out as snow. So essentially the snow, pretty cold cloud top temperatures, they fall into that little bit of shallow warm layer. This is not a huge warm layer, but a shallow warm layer, and it kind of partially melts that snow. So what you basically have is a drop with a slushy core, and essentially that refreezes into a deeper cold layer below. So there's going to be about maybe 500 to 1,000 feet right below where that deeper cold layer starts. You're going to have drops with a slushy core. I can guarantee you that's going to freeze on your airframe very quickly, and we know they're probably going to be larger drops just because how they're produced. Last but not least, we'll talk about the 3,000 foot rule. Now, I remember when I first started to learn to become a pilot and eventually a flight instructor, I remember somebody telling me back in the 90s when I was working on my private pilot certificate that says that if you encounter icing conditions while you're en route, a simple climb or descent of 3,000 feet will usually allow you to exit those icing conditions. And I'm a little bit skeptical of any kind of rules of thumb, especially with icing. So I thought, maybe there's something to this. So I didn't want to completely dismiss it. So I took a look at it, and it turns out that it actually is quite true. So in non-convective weather systems, so we're not talking about these deep cumulative warm cloud kind of systems. In non-convective weather systems, usually we're dealing with nimbostratus, which are highly layered. And so there are altitudes between these cloud layers where there's clear air, essentially no clouds at all. So you might be lucky enough to pop into one of these clear layers. And certainly even within the clouds themselves, you may see that the cloud structure itself may only be 3,000 or 5,000 feet thick. So again, if you're in the middle of that cloud deck, you may be able to pop out on top or even descend below. And the other aspect is that even within a cloud with a continuous layer of liquid water that's below freezing, you may find a little bit of different maximum minimums in that cloud layer. So again, you may be in a situation by just changing your altitude by a couple thousand feet, you may not necessarily stop accreting all ice, but you may lessen that ice situation there. So if you look at, this is a study that was done by Environment Canada, And if you looked at what essentially is called the continuous supercooled cloud layer depth, so think about, where they were flying through clouds, and when they found where there's supercooled liquid water, not necessarily where the edge of the clouds were, but where they found supercooled liquid water, how deep was that layer? Well, it turned out 52% of them were about 1,500 foot deep, and even 26% more were 3,500 foot deep. Again, you're dealing with almost 3/4 of the amount of these layers, where by changing your altitude by 3,000 feet or so, you're going to essentially get out of the supercooled liquid water situation. Now, last but not least here, exiting ice. What do we do here? Well, I think there are really kind of two surefire methods when you find yourself in icing conditions. And one is to climb or descend to an altitude that takes you to cloud-free air or precipitation-free air, or a climb or descent that takes you to a static air temperature that is warmer than 0 degrees Celsius. And this is where you're doing your homework ahead of time. Hopefully you're not running into this because you've done your homework, but essentially knowing where that freezing level is, knowing those kind of things will really help make these decisions a lot easier if you're hit with a surprise, per se. So essentially, both of these kind of situations will eliminate any further ice accretion. But I've been told by a number of people, and I've read a lot, that it's okay to try to climb into colder air. Remember, as you get colder and colder temperatures, you're probably going to get less liquid water and more ice crystals in those clouds, especially near the tops. I don't always like to depend on that, because number one, if you have to climb, you're going to start slowing down, and the longer you're in those conditions, the more ice you're going to accrete, just because you're in those conditions for a lot longer. So as you continue to climb, you're also you're increasing your angle of attack. We find that most icing incidents and accidents start to happen when you increase your angle of attack. That stall speed starts to increase because you're collecting ice, and your stall speed and your actual speeds eventually start to meet with each other, and that's when you get yourself into trouble, lose control of the airplane, and bad things happen at that point. So I don't really like the climb into colder air approach. Certainly, if you happen to be dive down into a cloud deck, you're trying to do an approach and land under IFR, and you end up in icing conditions, well, certainly climbing back out is probably the best method in that case, because just above that layer you were in essentially ice-free air. Now, so if you're accreting ice, I like to tell pilots it's always better to do something. Don't ever think that staying in the ice at that particular altitude and on that same route is going to something's going to change with it. Most likely it doesn't. So you're going to always want to do something, whether it's climbing, descending, and my favorite thing to do essentially is to turn around. I'm the best pilot report. If I start picking up ice, and I know that 5 miles back I wasn't picking up any ice, that's where I'm going to essentially try to go. So by turning around, I'm putting myself in a position where I know within the next 5 minutes or so I'm going to get out of that ice because I was just there. Well, thank you very much.